Hopefully you've had an opportunity to try these practice problems. I'm going to walk through this solution. So these are the different molecules we've been tracking through our practice problems. We've built their Lewis structures. We've built them in 3 dimensions. Now we're going to assess their polarity. So I'm going to go through, and I've already copied the structures onto this one. And I'm going to identify the polar bonds and then take the vector sum to decide if it's a polar or nonpolar molecule. So let's start with identifying our polar bonds in our first one, A. So carbon and hydrogen are always nonpolar. They have an electronegativity difference of 0.4. Carbon-carbon has an electronegativity difference of 0. So I'm going to put that over here. However, my carbon and fluorine have an electronegativity difference equal to it's 4.0 minus 2.5, so 1.5. So I can identify polar bonds along that fluorine right here. So now taking the vector sum of this, I could see they don't perfectly cancel out at all. They're both kind of pointing down in the same direction. And honestly, anytime you have a single bond, it's spinning around that bond so much. It's like, they're kind of like, where is it in space? And we'll just go with the way you drew it. So I'm going to have an overall dipole moment going like this. And I would call this molecule polar. All right, moving on to my next one. So my carbon-carbon bonds I've established are nonpolar. My carbon-hydrogen I've established are nonpolar. My oxygen-hydrogen bonds, however, are going to have an electronegativity difference of equal to 3.5 minus 2.1. So that'll be 1.4, I think, if I can do math in my head. And my carbon-hydrogen bonds, my carbon-oxygen bonds are going to have an electronegativity difference equal to 1.0. So I have a polar bond between each of my oxygen-hydrogen, pointing at my more electronegative element oxygen on both sides here. And so there's some component of these vectors that cancel out, but overall they all have kind of a downward motion. So there's going to be an overall small dipole moment pointing down on this molecule. And so I would also call it polar. All right, moving on to C. So carbon and hydrogen we've established as nonpolar. Carbon-carbon, nonpolar. Now carbon-nitrogen is going to have an electronegativity difference equal to 0.5. So it's right on the edge, but we would consider this a polar covalent bond. Our hydrogen-nitrogen bond will be polar as well. It'll be equal to 0.9 for its difference. So I have 3 polar bonds. They're all kind of pointing in at that nitrogen, which is the most electronegative element. And so they don't cancel out. A small component of those vectors cancel out, but overall they don't. And I get a small dipole moment pointing at those lone pairs for a polar molecule. Let's look at our next one. So phosphorus and chlorine have an electronegativity difference. So phosphorus is 2.5 and chlorine is 3.0. So this is going to have an electronegativity difference of 0.5. So we'll call it polar. It's right on the edge, but it's polar. And those chlorines are more electronegative. So the dipole arrows I'm drawing are pointing to the chlorine. But now I'm seeing that these 2 right here on the top and bottom, they cancel out. And the 3 in the equatorial plane are all 120 degrees apart and pulling equally away. So they cancel out as well. So there's no overall dipole moment here at all. So this is non-polar. My next one, last one, phosphoric acid. So my phosphorus and oxygen have an electronegativity difference greater than 0.4. So I'm going to have a dipole arrow that points to the more electronegative element oxygen at 3.5. So I can put those in. And I've already established that oxygen and hydrogen have a polar bond, and that's pointing at my oxygen. And so while all of these bonds are polar, and I can definitely say that these 4 right here around the phosphorus cancel out, I can't say that the ones around the oxygens do though. And so it looks to me the way I've drawn it, and you might draw it differently, that there's a little bit of a dipole moment pointing down. And so I would call this a polar molecule.